Today, the webinar is being focused on the application of soil compaction in the geotechnical engineering. Through this webinar, we will be covering the topics of soil mechanics, in which we will give a basic introduction to soil mechanics, compared, and with that, we will be talking about the compactions, its purposes, principles, compaction curves, and compaction methods. Most of you might be aware of it, but I'll be still refreshing the same for better understanding. And going ahead, we will be just briefly talking about a few laboratory tests which are applicable for the soil compaction and determination of the same, and few specifications, and how we will determine the field unit weight of compaction during the course. And at the end, we will discuss a practical case study which will give you an insight of how this basic principle of geotechnical engineering is very important and applicable to all kinds of civil engineering and geotechnical projects which are happening all around the world. So, to introduce to soil mechanics, it is an area of expertise where we need to determine the definition of the soil. Soil mechanics is studied even by a civil engineer or a geologist. But for a civil engineer, soil is a material which is used to build on various buildings like tunnels, basements, roads, dams, etc., etc. And a civil engineer studies the properties of these materials. Whereas for a geologist, it is a different material in terms of how the soil is formed, how things are happening in and around in the geological action of the planet. The soil has mechanical properties which are majorly the concerns for the engineers, which will look in terms of the permeability, stiffness, strength, and also depending on the nature of the soil size, the stress and the water content and the unit weight is also being studied. Soil compaction is basically a method where we increase the soil strength, characteristics, and also enhance the bearing capacity of the foundation that are constructed over them. Increase in the soil slope stability of the embankments, and it is also the amount of the undesirable settlement of the structure is being reduced. So in the figure below, if you can see that this is an example of a poor compaction, and this is an example of good compaction which is happening, and it helps to increase the bearing capacity and also increases the durability. One of the other examples, which is the second figure, where you can see due to the higher resistance of deformation, it can cause damage. So we need to have a good compaction in this area as well. The third is also, it is giving an example of how if the soil compaction is increased, stability gets increased, and it also decreases the permeability in the soil. So moving ahead, basically we should also know what is the purpose of this soil compaction. The soil compaction is also used to increase the strength, reducing the permeability, and reduces compressibility, controls the swelling and shrinking, reduces liquefaction potential. So, what does this mean that increase strength? This means the larger loads can be applied to compacted soil since they are typically stronger. So, increased shear strength means increased bearing capacity, slope stability, and pavement system strength. The reducing permeability, this inhibits the soil ability to absorb water and therefore reduces the tendency to expand and shrink and potentially liquefy. And in terms of reducing compressibility, this also means that the larger load can be applied to the compacted soil since they will produce smaller settlements. So the basic principle of compaction is reducing the void volume, which is achieved by the compaction. During the process of compaction, neither the volume of the solid nor the soil grains are reduced as per assumptions. And this is determined by a formula where gamma D is equal to gamma W, and the specific gravity of the multiplied by the specific gravity of the soil plus 1 plus E, and E is the void ratio. And if you can see in these figures, in the first place where we see soil, it present before compaction, and once the granular grains are compacted, they bind into each other and giving a good compaction. Similarly, when the soil grains are rounded, you can look at them that they are a little bit of scattered, but when they get compacted, they fall in place and give a good compaction things. Why compaction is important? Because the compaction effect of the air, water, and solids has to be in a proper ratio so that it gives a good basics to the structure on which they have been constructed. And this is studied through a compaction curve, where if you can see in the first figure, where it has been explained that the dry density increases with the increase, the dry density increases with the increase in water content till the gamma D max, that is the maximum water content. And this density is attained with further increase in the water content. And once this happens, then again the density starts falling. So we need to determine this optimum moisture curve, which is also called as OMC. So the optimum moisture content is one of the important aspects in compaction. Similarly, if we move ahead to the next figure, wherein the compaction curve, the water content is corresponding to the maximum dry unit and the weight is called this optimum moisture content. Note the maximum dry density unit is only maximum for a specific compactive effort and the method of the compaction. In the third figure, the each compactive effort of a given soil has its own optimum moisture content. As the compactive effort is increased, the maximum density generally increases and the OMC decreases. So this is shown in this figure where the optimum moisture content OMC1 and OMC2 has been described. So similarly, based on various materials which are used in a particular structure or embankment or road, the line of optimus is being tried to determine where the peak points of the several compaction curves at a different compactive efforts for the same soil will almost be parallel to the zero air voids, where S is 100%, and this we never achieve actually. So, as we were talking about the compaction methods, in general, these are the compaction methods which are being used, wherein the coarse grain and the fine grains are soils are available, and in the laboratory they are determined using vibrating hammer. And in fine grained soil, it is in the laboratory we are using falling weight hammers, kneading compactors, a static loading, and press. In the field, the hand operated vibration plates, motorized vibration rollers, rubber tired equipments, free falling weight, dynamic compactions are being used. In case of kneading, we will be using, in case of the fine grained soil, the hand operated tampers, sheep foot rollers, rubber tired rollers. So this is just a brief about this laboratory test, which has been used for compaction testing. Initially, it was started with the standard Proctor test, and it is not considered sufficient for the airways and highways. Whereas to determine that, there was an increase and there was a modification in standard Proctor test, and later on adapted as ASTO and ASTAM. So if you look into the summary of the standard Proctor test and the modified Proctor test, in standard Proctors, we are generally using 3 layers and 24.4 Newton hammer, whereas in case of the modified Proctor test, we are using 5 layers and 44.5 Newton hammer. And other than that, there is a difference in the energy which has been used, and hence modified Proctor test is largely followed in the industries these days. And coming to the specifications of the field compaction in general, the dry unit weight is basically, they say we have to achieve somewhere between 90 to 95% of the max dry weight unit, and has to be done for all the earth specifications by any contractor or any person who is constructing that. And it should be determined in laboratory by either standard or by modified Proctor test, as we discussed earlier. So here the relative density R is equal to gamma D field and gamma D max lab into 100%, which helps us determine that. And we should also note that the relative density and relative compaction are not the same. The correlation of the relative compaction R and the relative density dr is given by the equation which is being given below. So moving on to the determination of the field tests actually. So these field tests in this method will here I've shown three basic methods where in field we try to determine how the compaction has happened and how good it is. So there is the sandport method, rubber balloon method, nuclear method. So the advantage of the sandport method is you need a large sample and it is much more accurate. In case of rubber balloon method, the sample is large and direct reading is obtained and open graded materials are being collected and tested. Whereas in case of nuclear method, it is fast and it is easy to redo and more tests are can be done at the same time and it is statistically more reliable tests. And the disadvantage of the sandport method is there are many steps, large area is required to conduct this test in field. It takes time and it will stop all other activities. It will halt the equipments while the sandport method is being done at field, and it will be tempting to accept the flukes which happens most of the times while you're doing it on practice. Coming to the disadvantages of the balloon method, it is slow. There is chances of the balloon breakage, and means you may not feel so comfortable, and it becomes awkward sometimes in the field. Coming to the nuclear method, we basically in the nuclear method don't collect any sample. The radiations are being used, and the moisture suspect is one of the disadvantages in the nuclear gauge method. And means although it encourages amateurs to carry this method, but again it has its own means limitations and workability. And one of the most important factors is the error determination. In case of the sand cone method, the void underplate, sand bulking, compacted, and soil pumpings could be the error which will lead to some of the determinations. And in case of the balloon densometer, the surface, if it is it's not level, soil pumping and the void under the plate will generate errors. And similarly, in nuclear gauge, it can be miscalibrated. Rocks can come in between the path, and surface preparation is required to carry out this test. And it's a backscatter. And coming to the one of the most important factors is the cost. Okay, sand cone method is a low cost method. Balloon densometer is a moderate method, a moderate cost means testing, and nuclear gauge is very costlier affair. Based, it depends on project to project. Like people don't use too much of nuclear method, and if it is a very small project, they try to work on sand cone methods. And in practical applications, since I told you there are chances of errors, so industry experts they use minimum two methods to determine the compaction of the same in the field. Now, we should move ahead with the most interesting part of this webinar, that is the case study. So, giving a brief about this case study to you, this is embankment study in a location where a aluminum refinery is leading out the waste into a tailing pond. So these residue embankments, that is J1 and J3, where the residue of the plant, which is in the form of a slurry, which is say semi-solid and with too much of moist, it is mixture of few solids and means a few liquid things which are available. This case study basically deals with whether this embankment, whatever J1 and J2 has it got enough compaction and whether it can withstand the tailings or the solids and liquids which is getting collected into that area through a aluminium refinery which is placed nearby. So although this two J1 and J2 areas in J1, the external perimeter embankment was to retain both the red mud and the liquor in order to ensure the water tightness of the embankment. The J1 embankment was constructed by roller compaction of the red mud to specified field density of 95% of standard mean dry density, that is called as SMDD, and with no value below 92% of SMDD. The second area, that is J3, is an external perimeter embankment required to retain the red mud and liquor and was constructed using simple dozer placement and the compaction of the dozer track rolling to a target density of 95% SMDD and with no value below 92% of SMDD. So the preliminary assessment of this construction of these trial embankments and the general assessment of the suitability of using of the red mud for the embankment construction is presented in this case study here. And one of the earlier findings was that this needs to be satisfactory and target undrained shear strength should be 40 kPa minimum. But since we are not talking about shear strength here, I'll be restricting myself to the soil compaction only. Okay, and there were other seismic conditions were also being studied in this project. This is the basic outline of this. So these kind of practical examples or practical problems are often have to be dealt by geotechnical engineering experts in the field, wherein there is something which has been constructed and you need to understand and give solutions if there is any problem. So there was a recommendation as a part of this study, which was said that you have to carry out a cone penetrometer testing of the embankments and to assess the in situ strength and of the embankments and the foundation. This is the X section of the area J1. So in the area J1, the compacted red mud is referred to be very stiff, clayey and clay still. A typical cone tip resistance, that is QC values, range from 2.5 to 6 MPa, means with an average mean of 5 MPa. And to correlate this with the shear strength value of 125 to 300 kPa, that is around mean of 250 kPa. So you note that the J1 trial embankment constructed using the compaction practice of the red mud, the ripping of the red mud for drying prior to the compaction, spreading the red mud approximately 40 loose layers by a scraper, and then compaction by a 18-ton sampling roller was being done. And when this was studied in case of the J3, we find that this J3 area, there the dozer compacted red mud is referred to be stiff, silty clay to clay silt, and the mean MPa was around 3, which was 5 in case of the J1 area, and the shear strength values mean was somewhere around 150, that is almost the same. And while the compaction practice followed in J3 embankment was spreading the red mud by dozers and compaction by dozer track rolling method. But in J3, what was found that the dozer compacted red mud has about half the in situ strength of the J1 roller compacted red mud. In addition, by the way of observation, the J3 embankment performance was inferior to the J1 because the trafficability, the J1 performed better with adequate access to two-wheeler drive vehicles, whereas J3 required all-wheel drive vehicle capability for the access. And in case of J3, since the soil which was used was little loose on the surface, and it was more prone to dust production and more susceptible to re-wetting with the rain. So if you look, these were the CPT results of area J1, and if you can see, like the resistance and the frictions and all these things look okay, and it is being done with the good compaction stuffs, and it is turned out in the study. Whereas if you see here, there is a little bit of a gap, and here the graphs which are going out gives us the indication that it is means constructed with various layers, and various layers which are being used in these kind of compaction. It does not really go through that well, although it achieves the requirement what was been said during the construction. So when you carry out this comparison of the CPT data from J1 and J3 areas, J3 doser compacted red mud, as I told earlier, had the half in situ strength, and the stiffness of the J1 roller compacted red material was better, and hence by this we can say that though in a same project two embankments were constructed using two different compaction methods, but one compaction method is superior to the other one, although both of these study of the embankments did not restrict or did not fail due to the work which was being done at the site, and it came with the conclusion that the CPT data, that the red mud embankment material which was used or had undrained shear strength in excess of the maximum 4 kPa required for adequate factor of safety against the embankment failures. A target dry density of 95% SMDT with no value below 92% would appear to be appropriate for the embankment stability and function as of a red mud embankment retaining both red mud and recur. And the roller compacted red mud had about double the strength and stiffness of the dozer rolled red mud material. So you see, while we are doing these kind of work at site, sometimes it happens that we need to have some ballpark methods to determine whether our soil has a proper moisture being given to it. So I'll be sharing one such practical method. It is called as the hand test method. Okay, and it is a quick method of determining the moisture density. So you pick up the handful of soil which has been used, you squeeze it in your hand, open your hand. So if the soil is powdery, it will retain the shape made by your hand, then it is too dry. If it shatters when dropped, it is too dry. If the soil is moldable and breaks into only a couple of pieces when dropped, it has the right amount of moisture for proper compaction. If the soil is plastic in your hand, leaves small traces of moisture on your finger, and stays in one piece when dropped, it has too much of moisture for compaction. Similarly, there are numerous things which are related with this compaction. One such was shared with you through this case study. And I would also like to inform you that during your courses of civil engineering, you might have heard a lot of examples of carrying out problems and solving problems of how much cost will a borrow area will do, or how much means moisture is there at the particular borrow area, or how many trips we require to do it. These things are good in your educational studies and stuff, but when you come to industry, there are certain established factors, established parameters, established things which we need to look, act fast, and give output to the industry. So, one such thing is you have to know what is the material. The material which has been used for compaction is one of the most important factors which helps you to determine and achieve the required compactions which is there in a particular project. Although, as I told you earlier, normally people say you have to achieve somewhere between 90% to 95%. That is what it is expected from everyone, to any contractor or any company which is building any embankments, roads, dams, and all these things. But on the same time, there are lot of cases wherein you will find that due to a basic errors, lot of projects fail. Many people think that this soil compaction study is not very important because building up structures, giving good foundations, and all these things are important. But I personally believe that though it is a very basic topic in geotechnical engineering and soil mechanics, it is utmost priority is given to it. And once we achieve it in field, whenever whoever is performing in any project, the results will be marvelous. You can look out for the compaction things even at your homes at certain places, because due to very bad compactions, you might see the buildings are developing little bit of cracks. It is not able to bear the capacity of what of the whole structure, because to build a small house, people don't do these kind of geotechnical studies. We carry out these kind of geotechnical studies to means look for very big projects or very big works. But even in small projects, even in small locations, these things are much more important, and we have to follow it always. So moving ahead with this, I have come to end of my session.